Here we go! We're all about osmosis in this video. Alright, osmosis. Big deal. Big deal. Osmosis explains where water's moving. Water's important for all the reasons that we've talked about before, right? Water is one of the reasons why life is possible. So, tracking and knowing where water is moving and why, incredibly important for understanding how living organisms function. All right, you ready? Let's do this. Okay, let's review some terminology, right? Solutions are a combination of a solvent and a solute. The solvent, most commonly in living organisms, is water. The solute is whatever gets dissolved in that solvent. Here we have glucose that's been dissolved in water. So the solvent is water, the solute is glucose. Okay, whatever gets dissolved is a solute. So we have two different concentrations of solutions here. A 5% glucose solution and a 10% glucose solution. Which one has more solute? Which solution has more glucose molecules, has more solute molecules in it? Has a higher concentration of solute molecules. Which one? 10%, right? It has 2 times the amount of glucose compared to 5% solution, right? More solute in that solution over here on the right compared to the 5%. Okay. You're like, okay, Holly, we get it. Move on. Why are we doing this? So, in these solutions, we're assuming that there's a solute and then the rest of it is water to get to 100%. So if there's 10% glucose solution, we have 90% of that solution is made up of water. We have 5% glucose solution, 95% of the rest of that solution is water. Okay, so our solvent and our solute will always add up to 100. We're going to use some special terms to talk about the differences in these solute concentrations in just a minute, but I just want to lay this groundwork first. When we're talking about osmosis, we're really talking about which side of a membrane has a higher solute concentration. Okay. So, osmosis. The number one rule of osmosis is water will move to an area where there is more solute. Water always moves to the side where there is more solute, where there's more stuff dissolved in that solution. So water is moving here. Okay, so what we've got one tube set up right here with the 5% glucose solution. The other side has a 10% glucose solution. And what we've done is we put a membrane in the middle. So this gray thing represents, it's a membrane. That the holes in that membrane are too small to let glucose through. So this glucose molecule can't fit through. But water's pretty small, so water can move. So this is a selectively permeable membrane. So water can fit through, but not glucose. So water, like other molecules, will diffuse to reach an equilibrium. Water will move to where there is more solute, or another way to think about it, water will move to where there's less water, right? There's 5% glucose solution here, 95% water. 10% glucose here, 90% water. Okay, so there's a lower concentration of water on this side compared to this side, so water moves to that side. Usually in osmosis, though, we talk about water moves to the side where there's more solute. So we measure solutions in the concentration of solute. So water will always move to wherever there's a higher concentration of solute. Okay, say it one more time. Water moves to the area where there is more solute until it reaches an equilibrium, until basically both sides here have the same concentration of solute. Got that? Ready to keep going? Because now we're going to use some special terms to talk about those differences in solute concentration. So when we're talking about osmosis, when we're talking about water moving across a membrane, we use these terms hypotonic, hypertonic, and isotonic to compare the solute concentrations of two different solutions. These are only used when we are comparing one solution by itself. This water that I have here in my water bottle, we would not use hypertonic, isotonic, and hypotonic just to talk about just the water. We're only using it if we were comparing this water in here to a second solution. Got it? Okay. So, we may have heard these prefixes before. Hyper means above. So like hyperactive, you have a lot of energy. You're higher than normal energy level. Hypo means below, okay, or lower. Like hypothermia, not enough heat, right? Below heat, below temperature. And iso means the same. We saw this before when we saw isomers. They have the same chemical formula, but different shape to them, right? Now we're going to take those terms, hypo, hyper, and iso, the prefix, we're going to add on a suffix of tonic or tonicity. When we're using these terms, we're talking about tonicity, which is a way of talking about the concentration of a solution compared to another solution. So, if a solution has a lower concentration of solute compared to a second solution, we say it is a hypotonic solution. If a solution has a higher solute concentration when compared to a second solution, higher solute concentration, we say it's a hypertonic solution compared to that other solution. If two solutions have the same solute concentration, the exact same, we say they are isotonic to each other. Okay, let's try it. Again, we have these two solutions, 5% glucose, 10% glucose. What do you think the 5% is blank compared to the 10%? The 5% has a lower solute concentration compared to the 10%, so we would say that the 5% is hypotonic compared to the other solution, compared to the 10%. Okay, vice versa. Our 10% glucose solution has a higher solute concentration compared to our 5%. So we'd say our 10% solution is hypertonic when we are comparing it to our 5%. Okay, so it's only in comparison. It's a relative term. Tonicity, hypertonic, hypotonic, isotonic, those are relative terms. They're only used when we are comparing the concentration of solutions. Okay, remember our number one rule? Water moves to where there is more solute. If water can pass through a membrane, it will move to where there is more solute. Okay, ready to see how this works? Okay. So, let's take a red blood cell. Okay, here's our red blood cell. The cytoplasm of our red blood cell is around 0.85% solute concentration. Okay. Let's say we put that red blood cell in distilled water. Distilled water has 0% solute concentration. Which solution, the cytoplasm of the cell, or the water the cell is in, which solution has more solute concentration? The cell, cytoplasm, right? There's a higher solute concentration in the cytoplasm than there is in the water that the cell is in. So where's water move? Water moves to the higher solute concentration. Water will move into the cell. Okay, so water moves to the hypertonic environment, to the environment that has the higher solute concentration. So this will cause water to move into the cell. That'll cause the cell to blow up, to expand in size, and if so much water moves in, it could cause the membrane to rupture. Okay. Hypertonic solution inside the cell. Water moves in, the cell explodes. Another way to say this is that we are putting the cell in a hypotonic solution. The cell has been placed in a hypotonic solution. Okay. How's that going? Let's try another example. Same cell, well, I guess different cell, but same solute concentration in the cell. 0.5% solute concentration in the cytoplasm of the cell, in the cytosol of the cell, basically. Now we've put this cell in a 7% solute solution, 7% sodium chloride solution. Where is there more solute? In the water, in the solution the cell is in, or inside the cell? Where is there more solute? 0.85% compared to 7%, which one's larger? 7%, right? So water will move to the area of higher solute concentration. Water will move to the hypertonic environment. So water will move from the cell into the solution. So we have placed our cell in a hypertonic solution. So this solution here has a higher solute concentration than our cell. So we say that this solution is hypertonic. So water moves to the hypertonic environment. Water will leave the cell, exit the cell, osmose out of the cell, and move into the solution. And guess what? That's also bad. That causes the cell to shrivel up. Okay? Loses water, shrivels up, and basically makes a little raisin that isn't very functional. Okay. So, very distinct things happen to animal cells when they are placed in different environments. We place a cell in a hypertonic solution, water leaves the cell, causes the cells to shrivel up, and they're not functional. Place the cell in a hypotonic environment, water moves into the cell. The cell ruptures, potentially. Not good either, dead cells. We put cells in an isotonic environment. Water is still moving in and out of the cell, but it's moving in at the same rate that it's moving out. Okay, so there's no net movement of water because this water's in an isotonic environment. The concentrations are already at equilibrium. So water's moving in, water's moving out, but there's no net change in the concentration of water on either side of the cell. Okay. So this is why, if you ever go to the hospital or whatever and you need to get an IV to basically up your fluid levels, they don't give you pure water and they don't give you like a 10% saline solution, right? What do they give you? Should like a 0.8 and 0.9 saline solution? Why would that be? Because that 0.8 or 0.9 saline solution is isotonic to our cells. If we gave just pure distilled water in an IV, create a hypotonic solution in our blood, it would rupture our red blood cells and we'd be dead. Or vice versa. If we give a hypertonic solution, if we gave like a 10% saline solution in an IV, create a hypertonic environment, and again, we're dead. Osmosis, water moves to the hypertonic environment. So figure out whatever side of that membrane has more solute, that's the direction water is moving.